Okay, I'll start. So let me share my screen. So you can see my screen. Okay, yeah, so I want to first kind of revisit this kind of a clarification on these things. I don't think my pictures were very accurately, they were completely accurately illustrating these things. So that's why, I remade them, okay, for at least a couple of those things. Remember that this example I chose to illustrate that G of yes, not every CTL formula can be is expressible in LTL. So the normal tendency is to drop these quantifiers. You would think that if you dropped the quantifiers, then you would be able to, what you get will be an equivalent form in LTL. Certainly for maybe, for A, you would suspect if you drop the A, but this was to illustrate that that is not the case in general, and you have to be careful. Nonetheless, here, we saw that they were not equivalent to the corresponding LTL formula. But I just wanted to take now a moment to describe in CTL what these various combinations of A and E and G and F would actually mean as CTL formulas. So is everyone convinced that this AG-AF of P is equivalent to GF of P? It exactly requires that P should occur infinitely often on all paths, okay, originating from the root. Is that a yes?
Yeah.
Yeah.
Okay.
Yeah.
Yeah. So that's kind of clear. And the reason that I've drawn these kind of contours or these cascades is two things I'm illustrating. Okay. First of all, on every path, it has to occur in every state. In every state, eventually, P has to hold it. And that's why you have these things. And as you can see, these things will eventually fold. That's another thing that I indicated for finite systems. So EG-AF of P really requires that only exist a path in which globally you have every state has to be such that AF of P is true of that, which means that from every state, on every path eventually P holds good. Okay. So that will, by virtue of that, it imposes at least on this path, since it says on every path, on every state, on that path you have to have AF of P, and that's why what it is imposing is that there exists one path in which P occurs infinitely often. See, on all the other paths, by virtue of the fact that, that it only requires that AF of P holds good. Therefore, it's enough if you have P eventually hold good on all of those paths just once, okay? But just on one of the paths, it requires, it ends up requiring that P has to hold infinitely often. And I think all these things, once you realize that what these at each level, it imposes a constraint on the state, okay? And that's, as long as you realize that, you will be able to distinguish, okay, and then convince yourself what exactly that thing means, okay? So is this clear? Yeah, so that's why this is certainly not equivalent to a GF of P, the LTL formula, which requires on every path that P has to occur infinitely often. Yeah, so I had left the other two combinations as an exercise, okay, just for you to think. Has anyone thought about it to give a description in your words? Okay, so let's go one at a time. What does a state satisfying EF of P signify in your own words? Anybody? What does it
There
mean?
is a path where eventually P holds from that state.
Excuse me? It is.
So from that state, there exists a path where eventually P would hold.
Correct. So there exists a path. I mean, there exists a path on which eventually there is a state in which P holds good. Okay, on which P holds good. Okay? So that's what it means. P is itself a state formula. Therefore, there exists a state. Eventually, at some point, there exists a state on which P holds good. So if that's the case, let's take the third one, EG of EF. So given that, what does EG of EF of P require of the state of which that formula is true? So that's how that you interpret CTL formula in a hierarchical way. Once you understand what the subformula, the states that satisfy the subformula are, you can express the meaning of the enclosing in terms of the enclosing operator. So what is EG of EF of P mean? So that's the second bullet. So I'm doing for EG of EF. So
yeah. So hello. So there is some path from the root.
Yes. Yeah.
Where from each point there exists some path from that point where P eventually holds. Essentially, I guess, yeah. So
And see, you take in terms of states. Okay, so there exists. This is true of a state. If there exists a path from that state, so of course we are applying it to the root, okay, because that's what we mean. But if you can even talk about any state in that.
Right, yeah.
So it is true of that state if there is a path originating from that state in which every state on that path, EF of P has to be true. Okay? So every state has to satisfy this first bullet constraint. Okay? So there exists, it's enough if there is a single path in which in each of those states, from that, there exists path. And that's why this is what it requires, okay? So there must exist a path such that, and that path should, every state on that path should be such that from that state, there is eventually P holds good. So as a matter of fact, so although I have shown here as though, this is one way of satisfying, okay, I've shown that. So, it is for example, all the cross states are in which P holds good. This is only one of several ways in which this can be satisfied, because obviously, because it is cross P holds good here. All these, the root and this next one, they all are also states in which eventually P holds good. So although it is not true in this state here at my cursor, but it is true that eventually on that path P holds good. That is one way. Okay, so that's what it requires. So you notice that on this, okay, so on the rightmost path from the root, I mean, P may never hold good, okay? But that's okay, because it only requires one path, okay, on which eventually P has to hold good. It's not even required that these crosses have to occur on that path, as long as some other path, because this is not the only path from the states on this path that I have marked. So even if, as long as the P holds good eventually on the other path, like here, it is okay. So actually on this path that I have marked, it is not necessary for this thing to be true that P has to hold good in infinitely often, like I've shown here. It's enough if, as long as some other path has eventually P holding good. Okay, so it's even weaker than the requirement is even weaker than what I have shown here. Okay, so in other words, this one actually doesn't even require that that on any path P has to hold good eventually infinitely often at all. Okay, it only requires that every state on every state be such that eventually P holds good. Okay, so is that clear?
Yes.
Okay, so you have to carefully analyze that. Okay, so just ensure that you understand that it is not just path constraints. At every step, it's a state formula. Okay, and therefore you have to ask the question, if every state on that path that the subformula should be true of. Okay, so that's what this thing does. Okay, yeah, do either of them ensure P holding infinitely often? So the answer to that is certainly not this one. Okay, and as you will see, even when you have AG, that it doesn't require that they hold infinitely often on any of the paths. Okay, so here is the a pictorial view of what AG of EF of P is. So just like I've shown here, on one path, the states have to be such that on each of them, P has to eventually hold good. Here, it requires that it be true on every path. Okay, so on every path. Now, on every path, it is not necessary P itself must hold good on that path. Okay, it is enough that this some path from that state on that P eventually holds good. Okay, so yeah, so this requirement like this here is imposed on all the paths. So as you can see, I have marked here an extreme right path on which none of the states P need to hold good at all, as long as these paths, that the other path that branches off from each of those states eventually in some state P holds good. And that should be true of all the states, all the paths originating from that. Okay, so while it imposes this kind of a restriction that eventually every state has to, there must exist a path from which eventually P holds good, it does not require that on every path P has to happen infinitely, infinitely often. Okay, and that's that's what this thing. So these two, it does not have do not impose any requirement on the thing. Therefore, this certainly 2 is stronger than 3. Okay, and both the previous 2 are also stronger than each of these two things, because if you you can convince yourself, okay, that as long as the other 2 that I was shown before are stronger than either of these 2 formulas. Okay? Okay, so that should give you an idea. So all this thing is mainly to kind of reinforce the meaning of what CTL formulas are and how they need to be interpreted. Okay, so one other clarification that I wanted, I think it was Diganta who asked this, question, kind of made a comment saying that and I kind of agreed with him, but that was not entirely correct. Correct me if I'm wrong, Diganta. So what you said was, okay, so the claim was that yes, of course, you could express in CTL that some state occurs infinitely often. Okay, so the fairness constraint that requires each state in each some state in each of these P1 through Pk have to occur on a path infinitely often. You could express that the G of F is same as AG of AF of a state. Okay, so that will require that every path has to be a thing. But the problem is that although AG of AF of P requires you, imposes the constraint that be fair path, but this implication does not. Okay, the model checking of this implied formula where phi is some other, is not the same, okay, as doing ensuring this. Okay, that's why. Okay, because this is trivially true. Okay, as long as this model checking this, the origin formula might trivially become true. As long as there are, P holds good, there are fair paths, okay, originating from the state. Therefore, but what it requires is inherently you need to restrict the fair paths, and then you have to say that every path, from that should be such. That's why model checking this, even though you can express, doesn't exactly correspond to model checking, restricting model checking only to fair paths anymore. Okay, so that's why CTL, strictly speaking, this constraint of having to model check only on a subset of paths that are fair, you will not be able to do. Okay, explicitly by making that making a formula through implication. Okay. So that's the point.
You will need some sort of stronger thing than CTL, like a CTL star or something.
No, that is true. That's true. But then you can't express it anymore. Yeah. So that's the point I'm making. Okay. Although individually maybe you can express some paths originating, or all the paths originating from a state are fair. You just cannot put that as a precondition, and then by model checking it, you can't ensure that phi is checked only on those paths. Okay, because these become state formulas. Okay, and that's why.
So that is.
Yeah, that's why.
That is because our quantifiers are over states and.
No. You're right. Explanation is fine. But what I'm saying is you cannot do CTL model checking.
We should be able to do something like is by saying that like we define a path formula that is valid only for fair paths, and then we make an implication in that path formula and then quantify over paths
Yeah,
or something.
I mean, yeah, some special treatment is required. So that's the point I'm making. Okay, so you cannot just use first, as you will see. We will first cover CTL model checking in the classical sense. Okay, if you are checking for all parts, I'm sorry, CTL model checking is kind of saying collecting states, okay, on which they occur. So when you do that, unless you go, specially handle this restriction on the paths originating from the states on which you want to check the rest of the CTL formula on, you won't be able to do. So that's all I'm saying. Okay, you can't willy-nilly just do. Okay, so this will be clear. Okay, so when we will talk about CTL model checking, so certainly this implication, whereas in an LTL thing, checking this one, restricting the model checking for a sub set of fair paths can be expressed within the logic itself. Here you cannot do that. That's all I'm saying. Okay. Therefore, it has to be treated at a meta level. Okay, not within the logic itself. So that's the point that I'm making. Okay, so I want to move on. So what I want to do next is to talk about, okay, any questions so far? Yeah, okay. So, yeah, there is one thing that I have not done yet, which I normally do. See, so far, I've spent a lot of time in comparing LTL, CTL, and then taking individual formulas in really corner cases to push you to understand the subtleties of the distinctions, subtle distinctions between these formulas. Okay, there's also this thing, if you're faced with having to specify a particular property of interest to a system, how do you then express them in the formula? It is kind of the reverse. Given a formula asking you what states satisfy that, what paths satisfy that, that part we have covered, okay? You also covered some typical properties like infinitely often, eventually, persistently true, and so on. But if you're faced with some arbitrary situations, how do you translate or capture that into the logic? Okay, so maybe I will, cover that a little bit, if not in the class, through assignments. Okay, so that we can, there are certain typical class of useful formulas of some realistic systems on which I want you to that I'll have some properties of that you can then, and I'll ask you to express them in each of these logics, LTL and CTL. Okay, so what I want to cover next is certain universality of subsets of these operators in LTL and CTL, and also some laws, equivalence laws between them. Some of which we will use to simplify in devising our model checking algorithm. So some of these equivalences are of importance, of significance when you you will see I present the model checking algorithms. Okay, so as we said, it is enough to have the in the LTL temporal operators FG. I mean, in general for CTL star, FG and R. I mean, F, G, A, and R can always be derived from the rest of the formulas and rest of the operators. And that's what I'm illustrating. So F can be expressed. So that is, in other words, it is enough to have U, E, X, and negation and R. So the first one you're convinced, I guess. F can be removed. It's just a special version of U, okay, until G of F is the same as saying that you cannot have any path on which eventually F can become false, okay? If there exists one such path, then G of F will not be true. Therefore, you're saying that it is not the case that there exists a path on which eventually F can be false. So now this is a state formula in CTL or CTL star, A of F. So this follows from the existential semantics of existential quantification. Okay, A, if since this here is quantifying over all paths, it means that there cannot exist a path on which not of that formula is true. Yeah, because this requires on all paths that formula will have to be true, originating from that state. So this we went through last time. So R can also be, it's actually a dual of the until operator. And I went through this and I don't want to go through it again. So R can be expressed in terms of until by pushing the as a negation. So, and the negation of the until operator can indeed be expressed in this way using until itself and G, and of course G can be converted into F and ultimately into U. And the reason for including R in some cases is that this has when you expand it this way, because it has multiple occurrences of not G, and especially you sometimes when you do model check, you want to get these formulas in a normal form in which negation is pushed all the way to the atomic level. If you do that, then you can see that this can have an explosion in the size of the formula. And that's why if you had the release operator included, then you can express U in terms of the negation of the path formula that has U at the top level in terms of R. Okay, so that is universality of the thing. So what is a negation normal form? A negation normal form of CTL star is one in which the negation occurs only at the leaves. Okay, so for example, this one is in negation normal form, whereas the first formula and the one on the right side is not. And this you'll see that we will use in LTL formula. This is one of the pre-processing steps that we will do before applying LTL model checking. And why? And these rules that I have, which I call as duality laws, allow you to push negation downwards into the sub-formula of any CTL star formula. Okay? So not of A of any formula phi is the same as saying E of not of phi. Okay? It's not the case that on every path phi is never true, then it should be the case that there exists a path in which not a phi is true. So that follows from the semantics of existential and universal quantification. Okay, so this one is the dual of that. This we have already seen. Not of G of phi is the same as f of not of phi. And saying that these all can be derived from the first principles by looking at the semantics of the operator as defined in the CTL formal semantic rules of CTL star. In this case, on path formulas, and you can convince yourself that this thing is true. So, so not of claiming something the same as saying eventually not of that phi becomes true, and vice versa here. Yeah, I should have had this right in the beginning. Not of x of phi is the same as not phi being true in the next state of the path formula. Now, this is what I mean when I say R is the dual of that not of phi until psi allows you to push the not inside by replacing U with R. And you can do the same thing with R with U. Okay, so this is here is where, okay, so here I'm expressing the negation normal form using retaining R. Of course, you can get rid of the R. You can directly express, as I showed in the last slide, the negation of formula containing U in terms of U itself, but that will have repetitions of these formulas. So this is the classical ANDing and ORing of this thing. So those things will let you convert them into a negation normal form. That is something that you should be aware of, okay, that you can push a not all the way down. So what are these things when applied to CTL operators? So there is a universal set of CTL operators. You can do with, I mean, it's not necessary to have A and F. It's enough to define all CTL properties in terms of EX, EG, EU, and ER. And as you will see, even ER is not needed. Okay. So using these duality laws that you actually saw, and here I'm kind of customizing to the CTL operators. So AX of F from the law that you saw of replacing A with E is this, not of E of not of X of F, but this is not in CTL form, so you have to push the negation even further down, and that once again there was a law to do that in the NNF rule. So you will get not of EX of not of F. Okay? F can be expressed in terms of U. AG similarly can be, you can replace A, the universal quantification, by existential quantification, by taking the negation and then pushing the negation through inwards to express AG in terms of not of EF. And you can get rid of this EF with this U operator. Okay, so I should have had one more level of thing. So EF, and from there you can get rid of the F to get in terms of U. So AF once again can be reduced to EG in this fashion. AFF of U is, you can either do it through R, or yeah, you can have it in this, and you can always replace R with U. Okay, so that's why you can get rid of E of R and then do it this way. Of course, there will be like it happened without R, you will have repeated, multiple instantiation of a particular formula when you push it. But as you will see, in the case of CTL model, for CTL model checking, this will not be that big a deal, because you will see CTL later that for CTL model checking, it is not necessary to get the formulas, the CTL formulas in negation normal forms, okay? Because as you will see, because they are state formula at each level, you can actually do the negation at each level without actually pushing during model checking, and you will see that, and therefore that this repetition of replication of these not G, multiple instances of not G, is not going to be that big a deal, okay? Because the model checking method does not require you to get the formula in negation normal form. Okay? So that's why sometimes, usually ER is, is thrown away. So what this will reduce is the model checking will have to just deal with these CTL operators, EX, EG, and EU, and the rest you can check by using this reduction rules. So finally, some other laws. Okay, these laws are of purely of interest from a semantic point of view for understanding. It's not that they require you to, they are relevant, important, or significant for model checking. But sometimes, if you want to prove equivalence between CTL star formulas, this becomes important. But and also they are of interest anyway to eliminate redundancy in your formula. So repeated G doesn't add anything for the expressive part. G of phi is the same as G. And F, multiple occurrence of F together, you can get rid of. And so is the case with U. I mean, this is kind of, yes, if you have phi either here or psi on this side, you can, get rid of them. As you can see, yeah, so phi until phi will actually mean that phi has to continuously hold it until psi. And once psi holds good, it doesn't matter what happens later. And that's why these things are equivalent. Similarly, you can get rid of A and E, repeated occurrences of A and E. They don't add any expressive value. Okay? And there are some distributive laws, and these are kind of interesting. And sometimes these, whether F distributes, over R, F distributes over R on LTL formulas, okay? But not over. And this is not true for G. Firstly, let's get to this. Is this formula, does X distribute over R? Answer that question first. We'll get to is X phi or psi equal to X phi or X psi?
Yes, right.
Correct. It is, yeah. Okay. So, yeah, it's actually, you see, this requires either, yeah, it is true. So because, yeah, so either one is true. So since the thing that's actually true, and that is true for F also. Okay. So even if, yeah, if f or psi is true, because one of them is certainly eventually becomes true, and therefore, so the first part, if this is f of I is true, then you will have f of I or psi is true. Whereas that is not true for G, okay? Because for G, phi and psi is true only when it requires that phi and psi be true simultaneously at the same point, okay? Whereas, right? So whereas G phi and G psi, they yeah. No. This is actually true, isn't it? Yeah, this is true. I'm sorry. This is true. Yes, this is not true for F. This is true for G, because yeah, it requires on every state, if since it requires phi to be continuously true and psi to be continuously true, therefore it is true that phi and psi will be continuously true. And X, as you will see, also distributes over U. Okay. But what is interesting is this distribution law of F and G doesn't automatically lift to CTL operators. Okay. As you can see here, AG of phi and psi is not equivalent to AG of phi and AG of psi. Why? I'm sorry, it is equal. It is equal. I'm sorry, this is true, but this is not true of EG. Okay, I'm sorry. Yeah. So yes, this G lifting can be done as long as you have A, but not when you have E. Okay. Why is what I'm saying is EG of phi and psi is not. When you replace A with E, this equivalence is not true. Can anyone guess or explain why?
Left side says that there has to be one path where both phi and psi hold for every state in that path. While the right side says that there can be two different paths where one in one path phi holds and in another path psi holds.
Exactly right. Yes. Yeah. Good. So this it can be true on two different paths, whereas here it requires that if it's replaced by E, then it has to be the same path. Okay. And somewhat for similar reasons. Here, this is this is true of E of F. Okay. E of F distributes over phi of psi, but it's not true for A of F. Okay. If you replace E with A, then the distribution property of R does not hold good. Yeah, it's kind of the similar thing in here. So here, if you had E, this is a system where EF, yes. So this is true of a state if it is eventually has, but if you replace with A, then it is not the case, okay? That if you have phi or psi, the A or B, then one side will be true, but the other side will not be true. Okay. Correct. Yeah. So you have to be careful when you put the quantifiers on around these temporal operators, and some of them will not carry through. Okay. I think that's all that I wanted to cover on these things. So what I want to move on now is to start kind of informally introducing, covering model checking. Okay, we will start with CTL model checking. and then move on to LTL model checking. So CTL model checking is much more easier to conceptualize and to understand. It's also much more, somewhat simpler than LTL model checking. Therefore, that is the first thing that we will do. Any questions so far? Okay. Yeah, so we are now into the chapter 5 subject matter from the Clark et al. Textbook. I hope you can see this, or I can make it bigger if indeed that helps. Does it help, or is that good enough? Okay, so well, you will have to deal with it. Okay, so first I want to make some observations about counterexamples. You see, remember that we classified the properties into liveness and safety based on the whether based on whether the witness to the violation of the property required you to have an infinite path as a witness, or you could just show the violation using a finite path. Okay, for safety, so it required only a finite path to show the thing. But what I'm claiming here is, which I in a rushed fashion I did. So here I will illustrate and then kind of convince you as to why every infinite counterexample of a property must be lasso shaped. By lasso shaped, I mean it has a tail and then a loop. I mean, it has a front tail and a loop later, a repeated section at the back, the tail. See, for safety, you can always, okay, given a violation. So I'm saying that every counterexample can be extended to this. Understanding this is somewhat important, useful before you understand how you can design model checking algorithms. Okay. So for safety, once you have, since you any witness to the violation, a counterexample is a finite length. After that, you can extend that anyway. So to make it an infinite path that has a lasso shaped. Okay, so you can always construct a lasso shaped path for safety. For liveness is where it gets a bit tricky. So, and all these things follow from the fact it's true for only for finite state transition systems, okay, as long as the universe of states is finite. The simplest kind of liveness property is this AF of P, that eventually some property holds good. So what is a violation of AF of P? A violation is an infinite path in which P is never ever true. Okay, that means that it has to be not P forever. If this path has states in which not P, P is false in all the states, since we have only finitely many states in the transition system, at some point, some state, one state must reoccur. Okay, so at some point, the same S, you must reach an M such that the Sn is equal to Sm. So from the original infinite path counterexample, you can always construct this lasso-shaped path where you will, So the next thing for that will be the same as this. I'm sorry, it has to go here, okay, not to N, but to the next one following Sn. So this feedback has to go here. So then you have, so you've constructed it, okay? Now the new counterexample may not have exactly the same states in the old counterexample, but it's still a lasso-shaped path, and I mean, it's a lasso-shaped, and it is indeed a counterexample. This is, yeah, this is just, follows as a consequence of the fact that you only have finitely many states. Now, you can see this very obviously here, but for other more complicated liveness properties, the length before which you can actually have the thing lasso can be more complicated. Okay, so for example, suppose you have this AGAF of P property. So that is saying P occurs infinitely often. So when viewed kind of recursively, what it means is that this one is like saying, okay, globally forever, you can never, AF of P is not true, which means that since that is AG, it's an AG property, what you have to have is at some, your witness has to have at some point a state in which AF of P is false. That is, not AF of P is true. So, but that will, from that point onwards, you will have to construct a counterexample similar to AF of P. So this is a counterexample to AF of P, and therefore, what you will have to have is from there must be another, given that you know how to construct for AF of P. So this is AG of AF of P. You will have to first have something. There must be a point where not of P will be will be in a lasso. Okay. So that's how. So the violation of AG of AF of P will can be constructed once again with a lasso of this kind. Okay. Similarly, this is a linear time property f of G of P, but you can see that you can construct for that. So this is a violation of that will be such that eventually you will have to have a loop thing where P is not P becomes true infinitely often. Okay, this requires that eventually you have to have P to be continuously true. So violation of that will be eventually there must be a loop in which so whenever you say not of P, so this G of P can be violated only if there is some loop in which not P is infinitely often true. And infinitely often true, something can be true, if you can find a loop in which you have not of P to be true. So not of P is infinitely often true, which means that P cannot be true forever. Okay, so as you can see, the length of this pre-tail, the head here can be different for different formulas, but you can always find a counterexample that is shaped in this fashion. So that's one key observation that you will have to notice and understand. Any questions? We'll see some of these things we'll exploit in our CTL model shaping. So I'll give the kind of an informal introduction through examples today, and I will do it. And when we present this, and that's how it is done in the book as well. So we use an approach which is first non-symbolic, or more explicitly, it is called explicit
Can you
state.
hear me?
What?
Can you hear me?
Yes.
My microphone was not working for a moment. I wanted to ask a question.
Yeah.
So we have proved that there exists a counterexample which is lasso shaped, right?
Correct.
We haven't proved that every counterexample is of that form.
No, that's what we did here. Okay. So given, yeah.
Not every counterexample will be of lasso form, right?
No, that's exactly what I'm saying. So every counterexample must
every-
be a lasso
You have
shape.
written that every infinite CX of property must be lasso shaped. That's why I asked.
Yeah, but if the counterexample is finite, then I can always extend and make it into a lasso shape. So that's a trivial thing.
So prove that for every property, the counterexample is one of the counterexamples is of lasso shape. There will surely exist a counterexample which is of lasso shape.
Correct. Yeah. So
Right.
you're right. This is what I've proved here. Okay. And we will later prove that you'll see that every part in a finite state Kripke model will eventually have to have something similar structure. Okay. Okay. So you're right. In this case, I have not exactly shown that, you know, from some counterexample, I've been able to get a lasso shaped counterexample. That's the proof that I given. You're exactly correct. Okay. So wait some more time, and you will see that actually every part has to, in a Kripke model, will have to have one of, you know, we'll have to end up in one of a finite set of these kinds of lassos. Okay. And that's also, and you will see, that's also the case. So with that, it may not be, you know, what I've shown is, so for every counterexample, there indeed, you know, you can construct a lasso. So this way of doing that I've described here may not be applicable for every counterexample. Okay. So once I show that every part in a finite Kripke structure will have to end up in one of these such lassos, those in infinite parts, the other side will be true as well, is what I'm claiming. Okay. Or do you think you have a counterexample? I agree with you that this proof, I only took one infinite, you know, a counterexample, and then I constructed a lasso shaped thing for that. That is true. Yes. Okay. So let's keep it at that, and then the other side is also true, is what I claim, and we revisit that. Okay. Is that fine?
Yeah, it's fine.
Yeah, so what are the basic ideas exploited? This is only for CTL model checking. So notice that every CTL formula has a finite hierarchy of nested CTL operators. Okay, so every formula of this kind, of this shape. So what we do is, this model checking algorithm basically computes the set of states for each sub-formula, including the formula itself as a whole. It computes you know, the set of all states that satisfy the sub-formula rooted at a particular CTL operator. So, and going, yes, okay. So first it starts with the whole formula. So it computes the set of all states satisfied with the entire formula, and then it checks if the initial state is, if all the initial states are included in that. Okay? And S phi itself is computed recursively by computing S psi for every subformula psi of phi rooted at a CTL operator in nested in phi. And we give the model checking algorithm by actually showing how this S of phi can be, and you know that a CTL property can always be expressed using EX, EU, and EG. Okay, the rest of the operators can be converted. We saw in an earlier slide. So it's enough to devise algorithm to process this for a subset of these operators for EX, EU, and EG. The others can be expressed as in terms of these things using the negation operators, and that's what we do. So I'm going to use an example to show this, okay, to illustrate this, and then, yeah, you'll see the formal algorithm as described in the book next time. Yeah. So consider this transition system, Kripke model, a P with P as the label. So the first step is, of course, for every label, you kind of, for the atomic atomic formula in the, for all the atomic formulas in the original formula, you label them. You label every state at which that thing is true. I have labeled also not P here, but just for illustration. So that you can do. So there are only finitely many states, and I'm working with, and I will show this, by showing it how it kind of works explicitly on a transition system graph. Okay. Now that way of doing and designing the algorithm is called explicit state model checking. Okay. Then later, we will see how we could do symbolic model checking by doing, by devising another algorithm by computing fixed points, okay? But as a first step, we will see how you can do that by labeling every state with these S phi's, okay? For which that thing is with the formula or the subformula for which that is true of that state. Okay? So to begin with, you start with the atomic thing. So you label all, and I've already labeled these states in which P, for which P is true and not P is true. Now let's see how you can label all the states in which EX of P is true, given the label for P. See, EX, what are the states in which EX of P is true? EX of P is true if, given a state in which P is true, you can figure out what states in which EX of P will be true. So it is true of any of the predecessors of S, for example, S0. So you look at, for each state in which P is true, you look at all the predecessor states, okay? So all of, in every predecessor state of a state in which P is true, EX of P must be true, correct? Because in that state, EX of P will be true. So for example, here, there's, for S0, there is no predecessor state, okay? But S1 is a state in which P is true, which has a label P. And S0 is a predecessor of S1. Therefore, you can label S0 with EX of P. So you go through all the states in which is labeled with P. So is there another predecessor for S1? Yes. S2 is a predecessor for S1. Therefore, EX of P is true there and should be added as a label for that. And yeah, S1 is a predecessor of S2, and S2 has a label P. Therefore, S1 should also have the label EX of P. So similarly, so what I'm doing here is first I've labeled all of them with P, and then for each of the states that are labeled with P, I go to its predecessors and label them with EX of P. So that's exactly the states in which, okay, for not of P, so obviously not of P, yeah. So that does not participate in EX of P, okay. But if you want to do EX of, yeah. So then once you're done so this you do for all states in your transition graph, okay. And so you're done with computing the labeling or S fine. So you've labeled every state for which EX of P is true. So I've also shown for EX of not of P. So that you do by doing the same analysis with over states which have labels not of P. So this is the only state, S3 is the only state in which not of P is true. So you label all its predecessor, okay? And this is an iterative process, okay? Once the predecessor is done, you'll have to do that for its predecessor until you have, no longer can add these. You've looked at all the in this case, there's only one step, X, okay? In general, you will see that you will have to do. So EX of P will require only one iteration over the transition graph. So not of P, so S3 itself is a predecessor, therefore EX of not of P is true there. And S2 also happens to be another predecessor of S3, and therefore EX of not of P is true in S2. And nothing else, okay? So this is how you do, and EU kind of works the same way, okay? Yeah. So if you want to do AX of P, you will use the equivalence, the duality law, to get AX not EX of not of P, and that you can actually do. So this is exactly true for those states. It's a complement of the set for which EX of not of P is true. In this case, that is these two states, S0 and S1. So you take the complement of those states in which EX of not of P is true. So EX of not of P is true for S2 and S3. So S0 and S1. So AX doesn't need to be handled, can be done by just taking the complementation. Okay, here I'm actually showing for F of P, but this you can extend that to in general for P until E of P until Q. So I'm doing it for now, showing it for EU, okay? So what you do here is, once again, start with the base with P. So if yeah, I think I should have illustrated for generally for Q until P, but nonetheless. So P, obviously f of P is true, you know, so you have to, if P is true in a state, f of P is obviously true in that state, correct? So then as the second step, after you have labeled all the states with P, you add f of P to every state in which P is true, because f of P is trivially true in that in those states. That's why I have added E of f of P, you know, for that. And then you do the same thing, okay? And after that, you have to then look at all the predecessors in which have been labeled as E of f of P, and see if you know. So you should add those states as well. In this case, there are no more. Okay, I mean, is there? Yeah, no, there's no more. Okay, so you know, so it kind of terminates here. But if you, in general, if you had longer paths which lead, in which you know, P may not be true, but you know, but it may lead to something that is P is true. Therefore, you will have to repeat this labeling procedure for all the predecessors of the newly labeled state. Okay, until you have the no more states in the transition graph to label. Okay. So that's how you do. Now, for EG, this is a bit more complicated, okay? Because paths satisfying, say here, you see it's for, you know, for EG, you will see that the states satisfying you know, EX and EU can be kind of accumulated by starting with P and then working your way backwards there, whereas EG requires a little bit more you know, complicated handling. Therefore, so here I want to end. I will discuss how you do EG next time, but I want to make a couple of observations that will actually be useful in devising a method for checking EG. So here, this is in reference to the earlier comment I made about, so this is an observation about the structure of paths in a Kripke model, finite Kripke model in general. See, every infinite path in M can be expressed as pi naught, you know, some prefix, finite prefix pi naught, followed by an infinite suffix pi 1, such that every state in pi 1 occurs infinitely often. Okay, this is what I meant when I said, okay, so every path has this structure. So in other words, what I'm saying is every path of a finite state system can be expressed in this fashion. Okay, there is a prefix. See, the reason informally this is true is because, you know, there might be some states which occur only finitely many times in any path. Okay, but the only way that when you have a finitely many states in your transition system, there must be at least one state which must occur infinitely often, or, you know, there must be at least one state. So what you can then, so you can always, given that, you know, once you wait till all the states which only occur finitely many, you wait, and that you have accounted for in pi naught, then you will have all these rest of the states, which in some pattern put together will occur infinitely often. So this pi 1 through pi n, the states in them together are the states that occur infinitely often in the Kripke model. So what I've done here is I've kind of exhausted all the all these states that occur finitely many, and after that you only have one of finitely many ways that patterns that have to repeat infinitely often. This kind of answers the person who asked the question. Okay, so this is what, so every path can actually be expressed in this fashion. Okay, and you can see that this one is indeed kind of a lasso. It's one of different finitely many different kinds of lassos, but these are all finite patterns that repeat, okay, involving those states which occur infinitely often. You see, significantly, these kinds of patterns cannot occur, okay, in a finite state Kripke model, because we have imposed finite stateness. So for example, so this, yeah, you see this one where, you have some, repeated pattern of pi 1 followed by another pattern of pi 2, equal number of times, okay, for any n, that itself repeats infinitely often. Those kinds of things are not, you cannot, is not possible. And the reason is, just imagine, so you kind of compare this with, I'm expecting that each of you has had theory of computation, correct? So, these kinds of patterns can only be recognized if you have a push down, it's a language, okay? So since your transition system can only have finitely many states, it cannot produce these kinds of patterns. So you will need some stack there which can grow, in an unbounded fashion. So that's why there's pretty much pi naught is kind of regular, some finite, and this one is a regular language. You can see pi 1 to pi n. So that then you have some omega. So more, and so this will kind of gives you a pattern. So this may, you can only have some tail plus one of different ways of a pattern that occurs infinitely often at its tail, okay? And you can actually construct, and since there are finitely many, you can do this in such a way that these states which occur infinitely often, they'll have to occur in a strongly connected component in the in your transition system, okay? So the only way you can have these patterns occurring infinitely often is possible only if one of the states, the combined set of states in these things, are in a strongly connected component, and that's what you'll exploit in order to check, label states which have for EG of G, I mean for checking EG operator, okay? So I'll stop here unless you have any questions. So I will talk about this more next time, okay, when I look at EG and then show you a formal description of the algorithm. Any questions? I'm going to stop here.
So I had just a small question. So I mean, in so the in MuSMP, the examples that we saw, there somehow the counterexamples were coming out to be in a form of, say, pi 0 and then pi 1 to the omega, right?
Pi 0 followed by?
Some pi 1 to the omega, instead of having, say, some pi 1 plus pi 2 to the omega. So is it possible to, in general, always produce a counterexample where we have like a loop of some finite path going on and on?
That's what this thing is, no? This is exactly I'm saying. So these are all finite, okay?
Yeah, but then, I mean, so in this expression would also include parts of the form, say, pi 0 and then, say, pi 1 and pi 2 are alternating with each other, right? But in general, we should be able to...
Yeah.
Or some say like pi 1 and then pi 2 and then pi 1 twice and then pi 2 and then pi 1 thrice and then pi 2 and so on.
No. You see, so eventually it has to end up. You can do that some finitely many times, okay? But the infinite part will have to have one of these things. So we can have one, you have to make a choice. Eventually, some pattern has to repeat, okay? This is what I'm saying. You cannot have, this is the simplest kind of end. See, you cannot have, for example, first I will repeat pi 1 2 times, then 3 times, then 4 times, then 5 times, then 6 times, then 7 times, okay? So those kinds of things, if you want to generate those things, actually these things have to be generated by your model. No? So you will have to then keep some information in the state in order for you to be able to generate that, okay? That will require, you will end up having to remember some, you cannot do with just finitely many states in your transition system. So that's what I'm saying, okay? What you can have is all these things in various fashion, okay? I mean, in this, for example, you cannot see this is a transition system. So you have to be able to define your transition relation in general so that you will be able to take care of that. Yes, you can do this one, there is a pi 1, here, and there is a pi 2 here, okay? You can do those things, finitely many times up to a certain point. After that, you will have to do these things or that thing, infinitely many times, okay? So that's what I'm saying. So otherwise, you end up having to, So that's why, that thing is generating only those kinds of things, because your transition system can only remember finitely many ways of branching and doing it. And therefore, you may be able to alternate between these two things up to a finite thing, but the infinite tail will have to be one of these patterns repeating infinitely many times. Yeah.
So suppose we consider some, I'm giving like a particular transition system. So
yeah. So can we, since we are closing in on 5, can you hold your thoughts? I mean, if it is quick, then I will do. So let's continue this, okay? So if you, so I guess your question is that you're not fully convinced that a finite state system cannot produce a path. I mean, it can produce a path in which you can have pi 1, pi 2 arbitrarily long. I mean, you can keep circulating.
Yeah, so what I'm thinking is maybe we should, I think it should be possible for a finite state system to produce a path where the tail isn't like a simple loop. So the tail is some pi 1 plus pi 2 to the omega, but then when we're saying pi 1 plus pi 2, we mean pi 1 plus pi 2 as like it can basically be something like at each iteration we choose either pi 1 or pi 2, but that choice can be made arbitrary. So yeah, that is what I'm thinking should be possible.
Yeah. What I'm saying is you can have pi 1 through pi n for finitely many times, but you end up having to, it cannot, you should not remember any like these counting kind of a thing. cannot happen, okay? As long as you don't have counting of the number of times those patterns repeat, etc., then the number of times these things are used, then it's okay, okay? You cannot
Okay, but then
count.
is, I mean, so is something like this allowed? So say if we have, so when we write that like path is of the form pi0 and then within brackets pi1 plus pi2 bracket close and then to the omega. So then we are that expression is including paths of the form pi0, then pi1, pi2, and then pi1 twice, then pi2, and then pi1 thrice, and then pi2, and so on, right?
Yeah, but they're already, you're guessing a certain pattern, no? How will you produce that?
Yeah, so I think that should be able to, like, so if you have a transition system where there are like two possible loops that both begin and end at the same point, then
Yes, you're right. So as long as arbitrarily they mix the two things, that it's okay.
yeah.
But you cannot count, okay?
So
certain numbers.
Yeah, there cannot be any pattern in specific way in which they can mix the two.
Correct. Then it's okay.
Yeah. So, but then when say mu-SMV produces a counterexample, right? It does produce like a simple loop. Say it does produce something like pi0 and then pi1, 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 and so on. So I mean, in my example, it's clear to see that like that will happen. But is that like generally true that we should always be able to find a counterexample of that example?
Yeah, that relates to the question that the person earlier asked, huh?
Right.
So that you can, if you can always, that may be true because of the reasoning that I gave there, okay? That that you can reduce them from that thing, okay? So even if you have those things, you can reduce them to violation can then be shown with respect to a single lasso, okay? In which you have,
So you're saying that
slightly more generalized structure than what was used there, okay?
Right, yeah. So I'm saying what was used there should be like sufficient to describe a counterexample.
Counterexample, correct, yes.
I mean, we can have counterexamples of this form, but then we should have at least one counterexample of that form.
Of that kind, which is much simpler.
Yeah.
Correct.
Okay.
Yes. Okay, any other questions? Okay, so we'll stop here and we'll continue this. And if you have, I'm sure there'll be doubts on these things, and I might not sure if I've clarified all of them, so we can certainly revisit it next time. Okay, we'll stop. Thank you. Bye.